Right now, the physical space you occupy, the room around you, and even your own body is constantly, imperceptibly stretching and squeezing. In 1915, Albert Einstein predicted that space and time form a unified, flexible fabric. When the universe's most massive objects, like colliding black holes, move through this fabric, they send physical ripples outward through the cosmos. These gravitational waves have a highly specific geometry. As they pass through Earth, they stretch space in one direction while simultaneously squeezing it in the perpendicular direction. Measuring this change is incredibly difficult. The distortion is tiny, often smaller than a single proton. If you try to use a physical ruler, that ruler occupies the very space being warped, meaning it stretches and squeezes along with the wave itself, leaving you with nothing to measure. Catching a wave that alters reality itself requires us to move past physical tools and find unbreakable cosmic standards. The first solution to this problem is LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is a facility built to use the constant speed of light as a measurement tool. This tool operates on a massive scale. It consists of a 4-kilometer-long L-shaped vacuum tube designed to act as a ruler for the universe. A laser beam is split and sent down these two perpendicular arms. Because the speed of light is an absolute constant, the beam acts as a measuring stick that cannot be stretched or warped by gravity. When a wave passes, the physical space in one arm stretches while the other squeezes. The speed of light remains the same, but the distance it travels changes, causing the beams to return to the detector slightly out of sync. This chart shows the frequency of the first gravitational wave ever detected, an event called GW150914. The blue line represents a distinct frequency spike that confirmed the collision of two black holes over 1 billion light-years away. However, LIGO has a strict size limitation. Its 4-kilometer arms are perfectly tuned to catch fast, high-frequency signals, which are the quick chirps created by smaller black holes. The true giants of the cosmos emit waves that are far too large and slow for any facility on Earth to catch. To find them, we had to find a detector the size of our galaxy. Some of the heaviest objects in the universe sit at the centers of colliding galaxies, supermassive black holes, billions of times heavier than our Sun. These giants create slow, rolling gravitational waves that can take years or even decades to complete a single cycle. Catching waves this large requires a detector the size of a galaxy, which forced scientists to search for a new kind of cosmic clock. They found that clock in pulsars. A pulsar is a rapidly spinning dead star that shoots beams of radio waves into space. Because they spin so consistently, those beams sweep past Earth with the precision of a perfect timer. The Nanograph Project, a collaboration of researchers searching for these slow waves, uses massive radio telescopes to monitor these distant stars. By observing a network of pulsars across the sky, they can track exactly when each radio pulse is supposed to arrive on our planet. When a massive gravitational wave rolls through the Milky Way, it warps the physical distance between Earth and these stars. This warping of space throws off the timing of the pulsars. Because the distance has changed, the radio pulses arrive at our telescopes slightly early or late. By precisely tracking these tiny timing anomalies, scientists proved that the universe is filled with a constant, low-frequency background hum. We have now mastered two very different ways to sense the universe: quick laser rulers built on Earth, and a galaxy-spanning web of clocks in the stars. Throughout human history, astronomy has relied exclusively on capturing light through telescopes to observe the universe. Gravitational waves penetrate all matter without scattering or losing energy, providing a new way to feel the universe vibrate. This new sense allows us to track events that emit absolutely no light, like the collisions of invisible black holes. Scientists may eventually use these tools to detect the ripples left over from the rapid expansion of the universe, just a fraction of a second after the Big Bang. The universe is a dynamic, vibrating fabric, humming with a cosmic symphony, and human ingenuity has finally given us